So, hello everybody, my name is Sarah Sparrow and I'm going to talk to you this morning a little bit about the impact of extreme weather on the energy system. So when we think about climate change and the energy system, we're used to thinking a lot in terms of reducing our dependency on fossil fuels, reducing emissions that will contribute to climate change, how we can make a nice sort of clean and resilient transition to kind of cleaner forms of energy. We get less used to thinking perhaps on how the energy system itself is impacted by climate change through changes in extreme weather. And that's what I'm going to talk to you a little bit about this morning. So if we think about a sort of a typical energy system, what the sort of main components of this are, we've got sort of various different factors. Here's just a sort of cartoon diagram here. So we've got sort of elements where we've got a city representing kind of demand, the use of power and energy. We've got an electric grid, which is looking at distributing and transporting that energy to the city. And then you've got different types of energy power generation. So you've got oil and gas, you might have thermoelectric power stations, hydropower stations, wind farms, solar farms, producing biofuels. But you also need things like refineries, and you need to transport kind of fuel or sort of petrol, diesel around so that we've got energy to power our everyday lives. So if we think about how it is that different types of extreme weather may impact on these different components. The first obvious one is kind of direct damage. So when you have a sort of big windstorm or floods or fires, then that might kind of disrupt various elements of these of this energy system and cause sort of shortage in supply or blackouts and these sorts of things. The other thing that can happen is during things like heat wave events, you get enhanced sort of resistive heating in all the electrical cables and wires. So when it comes to transporting electricity along our kind of distribution networks and transmission networks, then we've got a reduced capacity and reduced efficiency in these times. So we might not be able to transport as much power as we're used to doing under those kind of conditions. And equally, if we've got droughts going on, then our kind of production of hydropower and stuff may impact the efficiency of hydropower dams. Again, it can impact on kind of energy production as well. I guess the obvious easy one here is if you kind of think about those green energy sources, so you're thinking of the wind turbines, the solar farms, and biofuels. If you don't have very much, if you've got very cloudy days, then you're not going to get as much sort of energy generation from solar panels. If you don't have very much wind, or if you've got too much wind, then your wind turbines can't operate and generate power that we might need. And if you've got drought conditions going on or floods, then that can affect sort of growing of biofuels and things. But equally, if you've got droughts, then that might affect your hydropower generation and also sort of thermoelectric power generation. If you've got floods, it can also kind of impact even on oil, gas and coal kind of generation or production of energy. And so we need to think about how we optimise the mix of these different types of energy sources so that we can be resilient to these changes. If we then think of transport, how we go about transporting energy, this is your sort of tankers with maybe sort of petrol or diesel that you're kind of supplying to your local petrol station, that sort of thing. If you've got sort of damage to the road network or rail network, then you can't kind of do this as easily anymore. And equally, a big point is in certain countries, the river systems are used quite a lot for transporting kind of goods or along distances where they just don't have the infrastructure of large sort of road networks, or it's not really very practical. So they're very reliant on these. So if there's a severe drought in that particular country, then it can really impact on the amount of energy supply that they can get. The other thing, which is probably almost the hidden strain, if you like, on energy systems in general, is through changes in energy demand. So in terms of, we only need to think probably to last summer. In the UK, it was sort of very warm. Probably lots of people went out and bought air conditioning units, or were looking to sort of switch on air conditioning to give some respite to those high temperatures. And using, therefore they're using more power, so there's more strain on the electricity grid and the people managing it in order to actually meet that increased demand. And that also might be coming at a time when your transmission lines through the heat waves is maybe not being as most efficient, or doesn't have as much capacity as we'd had before. So in short, I kind of say that if you consider each of these individual components, I wouldn't say that any one of them was immune to the effects of extreme weather and climate change, and they can potentially impact all of these different areas. And just in case you're sort of wondering, well, is this something that is a bit hypothetical, how these things can do, or does it actually really happen? Well, yes, it does. Here's just a few illustrations. We've got sort of trees bringing down sort of distribution power lines. In this figure here, we've got a flooded electricity substation. You can interestingly see all the flood defences that they put around, but obviously these were breached, so that wasn't perhaps large enough in order to save the substation from flooding in that particular instance. We've got the catastrophic failure of a wind turbine, and also here, this one's a bit hard to see, but actually it's a fire that was started due to kind of electrical faults, I think, following on from a heat wave event. So if we now think about, well, what is it in terms of extreme weather that's kind of happening? Does this happen very much? In sort of almost by definition, if it's extreme, well, surely it's quite a rare occurrence of something that might happen. If we just look at this year for an example, over the world, I've just picked a few here. There were severe floods in northeast Brazil much earlier in the year. There was heat waves in India earlier in the year. As I've already mentioned, in Europe and the UK, there was heat waves and sort of ensuing wildfires that happened. Again, lots of heat waves in America. In China this year, they've experienced a severe heat wave and drought. So here we've got the Yangtze River that's actually sort of, some of its reaches are beginning to kind of dry up in this particular severity of the drought conditions that they've seen. And last but not least, the very recent floods in Pakistan. So all of these things kind of present challenges that may impact on us. And I just wanted to say, bring one other example back from sort of last year, which is in 2021, where there was a sort of a big drought, what we call a wind drought. So we didn't have very windy conditions in the summer of last year, and that meant that the wind turbine plant, offshore wind, were not actually generating as much energy as we had expected. And because of the weather conditions that were associated with these very still kind of conditions, were also associated with droughts, then that meant that our hydro output was also reduced. So actually, Scottish Southern Electric found that their renewable energy sources were reduced by 32% last year because of this. So it's a real effect, and if you think that you've got to kind of plug that gap using some other method in order to actually kind of meet the demands of people to kind of continue living in society as we see it at the moment. And this is really quite a wide-ranging problem. I would say that there isn't really anywhere in the world that's particularly immune from this. So I've already said extreme weather happens everywhere. But also, these are some examples from the World Energy Council in 2015. And they sort of categorise the globe into various different areas. And you can see in these pie charts that you've got the sort of primary energy supply cases in these different parts of the world. So you've got the sort of Middle East, which is predominantly through kind of conventional thermal energy generation, so fossil fuels. And then you've got things like Latin America, where you've got a really large proportion of hydro generation. So you've got very different compositions in each of these areas as to how they might be generating their energy for us to use as a society. But on each of these sort of numbered figures, there have been kind of recorded incidents of quite considerable disruption to the electricity and energy systems in these countries. And you can see that it really covers most of the globe there. So there isn't really anybody who's immune from having to think and understand how we're going to meet the challenges that these extreme weather events present to us. So what can we do about it? Obviously, we want to improve the resilience of the energy system. We want to make sure that it's very reliable for us all to use. Now, we've got sort of two options. We can use sort of what they call hard resilience, which is where you're really trying to make your particular energy asset, if you like, as impenetrable to the effects of these extreme weather events as you can. So this might be something that you'd be looking to do for a nuclear power plant or something, where you're really not particularly wanting that to be breached by an extreme weather event. But at the same time, perhaps we should be thinking a little bit more about embedding soft resilience into our energy system. And by soft resilience, what we mean is we accept that we're not going to be able to make everything strong enough or robust enough to withstand the effects of these extreme weather events. But we need to think about how we can build things so that they can quickly recover from these impacts, and we can restore supply, kind of energy supply quickly. And the way in which we can do that is to start to take a much more of a full systems view of the energy system. So where do we start? We've got a lot of existing infrastructure there around the world that's used for generating and transporting energy for us. So, we've only got so much money. How do we know where we're going to invest in improving this resilience first? Now, some of the way in which we can do that is using a technique called the extreme event attribution. And this is where we aim to look at principally climate observations or climate model data and try and assess what the effect of climate change is on the frequency and the magnitude of extreme weather events. The outcomes from these kind of studies are you've got several options. So either you can find that the climate change has made that particular event more likely to occur, less likely, or there hasn't really been any change in that particular area due to climate change, or perhaps our methods aren't quite there yet, and we just can't tell for that particular type of extreme. So examples of things like tornadoes or that sort of thing, which are very hard to predict in sort of climate models. So how do we go about doing this in terms of actually assessing what the sort of change in likelihood of seeing these extreme weather events is? And we've got several different types of approaches that we can use. So the first is a risk-based approach, where we principally take very large ensembles. So these are where we've initialized climate models with slightly different initial conditions to get a range of plausible values of what we think may have likely happened. And we compare simulations with the effects of climate change and without the effects of climate change to see how the frequency and the magnitude of a particular event has changed. There's also a mechanistic approach, and this is very much looking at sort of storylines and looking at causal factors, trying to disentangle what are the different things that have resulted in that particular extreme event or extreme impact that we're experiencing from that event. And this can be useful to enhance predictability of these particular events in the future. So here we might be thinking of things like large-scale climate variability, things like the El Nino Southern Oscillation, how that might be impacting on different areas of the world in terms of their weather and climate. Another approach is what we call a circulation-based approach, and this is somewhere between the risk-based and the mechanistic. So rather than defining, if you like, our extreme event by saying we've got so much rainfall in this kind of location at a given time, is actually saying, defining it in terms of the weather patterns that you're experiencing. And you can do similar sorts of analysis on that. I would probably say from an engineering point of view, we're not particularly as interested in why we've come up with that particular extreme weather. We're thinking about building resilience and how much worse it could get. So the thing I'm going to talk to you a little bit more now is the risk-based approach to doing this extreme event attribution. So as I said before, we run loads of climate models to look at say what is the likely temperatures for a particular heat wave that we think that might have occurred, simulating the world as observed. We can then run a counterfactual scenario. In this case, we've run one where we've removed the effects of climate change. So we're sort of saying, what are the effects, what's the change that we are currently seeing now today because of the climate change that has already occurred. But equally, you could use future climate scenarios to then see how these might likely change in the future. And so what you do is you kind of say, okay, well, I'm interested in temperatures that are larger than about 34.5 degrees here. And so we're very much interested in these tails of the distributions to see how the sort of likelihood of the probability of getting a temperature of that magnitude or higher has changed in the different ensembles. So we're really interested in the area under this curve here and how that might change. And you can see there's a big difference between how much you've got in the red and the green here. Another way of looking at this, I won't dwell on this too much, it's just a very different way of viewing the same distribution. So rather than sort of plotting a sort of range of temperatures, you've got the temperatures on the y-axis, and this time you've got the likelihood, if you like, of reaching that temperature or getting more than that. So that might be the 1 in 10-year event, or 1 in 100-year event, or this sort of thing. And we can do the same sort of thing here and put the same threshold on, and then we can see how the likelihood of that particular event has changed. So here, what was in the actual case a 1 in kind of 30 or 40 year event has actually turned into a 1 in 4 or 5 year event. So that means that we'd expect to see those kind of temperatures or worse every kind of 4 or 5 years, taking a sort of statistical view of things. I should say the advantage of looking at things this way is so that you can really blow up those tails of the distribution. You know, if we start looking here, you're interested in, you know, really these sort of small elements that are very, very close to the axis. Whereas looking at it this way kind of splays those out, so it makes it a bit easier to see what's going on. So we can kind of define a ratio, which is a probability ratio, which is then looking at comparing those probabilities of those particular extreme events happening. The other thing that's, I think, particularly relevant from an engineering point of view is, you know, if you're looking at designing a piece of infrastructure, you need to build a building or a wind turbine or whatever to withstand the 1 in 50 year event, then one thing that can be said is the 1 in 50 year event now is not the same as the 1 in 50 year event will be in the future. And so the magnitude of that may well increase. And so if we're thinking of enhancing our